an ad hoc mentorship session, if you need an advice, if you need some support, or if you need a reality check with the tech professionals. We have a book club. We have writing club, speaking club, career club, coding club. Right now you are part of coding club, and CV clinics. All these projects and events scheduled on our meetup.com group, and you can find it there. Also, all of these meetup events recorded, and you can find records on our YouTube channel. Our other project is mock interviews. We have a platform project. We maintain our own platform by ourselves with the leaders and volunteers. And if you need some industrial experience, if you wanted to try if you wanted to contribute to our platform, you can be our volunteer and join this project and help us to build the best product. Also, we have LeetCode study groups. Right now you are on a summer LeetCode bootcamp. A part of this, we have a just LeetCode study groups. You can choose what works better for you. We have an awesome system design track, ML track, and I think some events about the clouds. Volunteers. We have a different type of membership. You can be just our members and be in observant mode, join our Slack, attend our meetup events, and just get the knowledge. You can be our volunteer. Volunteers are those who help to organize offline events or online events. You can give a tech talk, speak from our behalf, contribute to open source, write our community blog, contribute to organize newsletters, support our programs, as I mentioned before, support platform project, or be a part of our mentorship program. We welcome any volunteers, especially for the yearly annual project, because every time we need all experience, we need hand in there. Feel free welcome to join us as a volunteer. Or what you will get as a volunteer. I think members have the same, but moreover, you will have the network opportunities, our things, be a part of a team, learning your leadership skills, or get your practical experience in participating in a project or managing a project if you need this. You will have recognition from us, and you can put it in your CV, you can speak in your LinkedIn, and this probably will increase your visibility if you need this, if you're looking for new opportunities, and do you think that it will contribute to your. Also, many conferences offer us tickets for volunteers to events, conferences, very cost effective. And thank you for listening to this brief interview. I invited you to start the hard code, LeetCode, and we're happy to see you here. Thanks.
Thank you, Lana, for introduction. So, folks, let's get started from as usual. Or we first let's take picture probably.
Yeah.
And then we will start.
Yeah, for taking picture, usually we ask him to turn on your camera probably for 1 minute if you have your morning routine already. If not, it's absolutely fine because this is the Saturday. You don't need to be in the cover mode right now. So just if you can do this, it will be nice. And let me see how to have, yeah, this one, this one. Щось не знаю. And right now I'm trying to see how to see everyone on a. I have no idea. This one. Okay, let me find the view for everyone. Lilia, can you help me here?
Yeah.
Yeah.
I can take it actually.
Yes.
1, 2, 3. Let's smile, folks. Okay. I think,
thank you.
yeah. No
Nice. Now you can relax and turn off cameras.
Yeah. I will mute you, Nona.
Yeah.
Or you mute it because I can't. Yeah, thank you. So yeah, let's get started, folks. I will start probably from introduction. Yeah, let's get started from questions from last week, and then I will cover some organization questions. Any questions from last homeworks? Any complaints? Also fine. I hope you enjoy these recursion problems. I see. Yeah, after class there was quite intense, many submissions. So I will count. Yeah. Yeah, sure. Because I see that now is like less people who is doing it. That's why we are not supporting. We just drop message on the Slack, and we will support language which is you need. Just because it's difficult to maintain so many languages, and currently we see there is not like that many people at the beginning who is still persuading and solving all the tasks. That's why we are doing a fixed number of languages. But yeah, if you're doing, just drop a message and we will include it. Okay. Okay, if no questions, I will cover what will happen next 4 weeks. First, we finish the medium weeks, which was 4. You still have a couple of weeks who haven't finished, because at this moment I see there is nearly 25 people who finished, and they will receive a certificate like we did for Easy Week. The same will happen for next 4 weeks. Yeah, it's fine. We will have like a couple of weeks starting from this, because we are also need to prepare to put names. You have your weeks to finish, and then yeah, we will probably need to collect names if we won't find from the previous batch. It's fine. It's fine, folks. Just try to finish. You have at least 2 weeks. So now we're in a hard week. In order to finish Bootcamp LeetCode on the time, because we were planning to include more patterns, but as the topics is growing, so it is difficult to explain during the classes, and that's why we decided to cover. At this moment, we're covering the second part of 3. Next week we will cover try, which is a different type of tree, which is quite popular anyway. LeetCode ask during the interview as well, and it's very organically to move from tree to try, and then from try we will move to the graphs problem. So the plan is that today tree, second part, next will be try, and next 2 weeks we will spend on the graph problems, introduction, and some medium problems on the graphs, because graphs is a very wide topic. And somewhere in the autumn, we will try to define how we are going to cover advanced problems. So this is the plan. Any questions? Okay. Yeah, just ask, Fox. You don't need to raise a hand. You can just ask.
Okay. Yeah, I just wanted to ask, I haven't joined the previous weeks. Is it still okay to join now, or is it better to sort of start from the beginning?
Do you have understanding about tree?
A little bit, yeah, but not, yeah, a little bit.
you can try stay. I will try also a little bit cover introduction topic from the previous. If you feel overwhelming, then we have recording session from the previous one, and you can watch this week as well.
Okay.
Because tree, try, and graph, they are very related to each other. It's not that they build on each other, but maybe because tree is a foundation of the graph as well, and try it's just different type of tree. That's why this kind of weeks, they are connected, I would say, honestly, won't lie. All previous week when we were covering topics, you could jump on random weeks. But if you just don't have knowledge about tree, so I would say yes, it would be difficult to cover next weeks.
Okay, thank you. I will watch the videos then. Thank you.
No problem. Okay. So I will share now my screen. Okay. I will share both. This is whiteboarding from last week. Reintroduction. And that's what we are going to cover today. Okay. Also, I think we will finish today a bit earlier than always. But let's see how it will go. Because today we don't have theoretical material, but we have two tasks, free tasks. I intentionally didn't put more, but let's see how it will go. From last week, just to briefly repeat what we covered. It will be convenient for those people who was as a part, and also for those who just joined us. So I introduced to the tree. Currently, we are covering just binary tree, regardless of the type of the tree. We cleared, we slightly touched that there is different types of tree, but currently we just covering the foundation of the tree. So it is binary tree, which just looks like this. I explained it how usually nodes of the trees looks like. Then we discuss some terminologies. What is the parent node? What is the child node? What is the age? We discuss what does mean depth, height of the tree. Also, we most of the time we were spending on the topic how we usually traverse tree. We can there is two main approaches how you can traverse. It's depth first search method when you're exploring all the nodes by starting at the root and moving as far down as branch possible before backtracking. So basically, you are exploring all the nodes. And there is another way how you're going to traverse tree. It is breadth first search, the node of tree level by level, that we're processing this way, all the nodes, level by level. That's why it's a level traverse. And this one is devise, depth first search. Last week, we covered only depth first search. We intentionally, we wanted to cover breadth first search, but we decided that it is enough, and I agree, to focus only on depth first search. In today's topics, we will cover breadth first search. This is my favorite. It's more intuitive and in my opinion, it's rather easy than depth first search. The one thing that depth first search, you can't replace breadth first search with to solving tasks. So you should understand when you use depth first search and breadth first search. As a part of depth first search, yeah.
Sorry, I was just going to ask, we have backtracking in depth first search. Do we have backtracking in breadth first search?
No, breadth first search, it is just iterative solution.
Okay.
So yeah, backtracking what it means that we are doing recursion, and then at some point we just backtracking back.
Yeah, so we won't have to do recursion in breadth first, right?
No, it is iterative one.
Okay, thank you.
Yeah. So yeah. Yeah, as Moina asked, I was okay. This was a part of anyway. I didn't include this part. Let's just then cover quickly what is the breadth first search. So in breadth first search travels the nodes tree level by level. It's processed not at the present level before moving to nodes at the next step. We're starting from the root, and then we're processing childs and another child. So this is the different how we're processing, because in depth first search we're starting from root and we're processing this way. So means not on this level. So for example, we're starting from 4, and depends which is traverse you will choose, because depth first search has 3 options how you're going to traverse the tree. But anyway, you will process 2, then 1 and 3 before you will switch to the right subtree. This is the difference from breadth first search. In breadth first search, you are processing not subtrees, not left and tree, not first left subtree or right subtree, but you are processing again level by level. That's why it's a level traverse. So for this reason, we're using queue, just because queue it is supporting first in, first out, and for depth first search, if it's not recursion, then we're using stack. Last, because the characteristic is different from for stack and queue. So let's focus on breadth first, just on this snip code, how it's usually processed. So we're using queue, we're entering to the queue loop until it will be not empty. We pop up the first node. We process whatever logic you need. Then we are checking if node has left and right. We are adding to the queue. At the queue level, they are at the top will be 2 and 5. You will process first them, and then you will adding another level to process. So this is basically, that's it about breadth first traversing. Is it clear?
Sorry, Lilia, what does deck do in the fourth line?
It is Python. So it's, I don't know if someone has background in the Python. Can you explain it, Fox? What is the queue? In Java, it will be a queue.
Because we said appending is adding to the queue, right? So I was
Yes.
wondering, what is the difference between that and the next q.append?
Here, you mean?
Yeah, that is there. We are adding the left child to the queue.
Yes.
But what is that line doing in this?
It is just a syntaxes of the Python. The main idea, you're just using queue and you are adding into queue. And the reason why we're using queue in breadth first search is because any elements which is you're going to process, you will process them in the order like first in, first out. Means you put your root first, and you will process your root first. Yeah.
Okay.
Yeah, it's just I want to add deck is just creating a queue.
With is it just creating a queue with root as its first element?
Yes.
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 Okay, that makes sense.
So this is just a syntaxes of the Python. I'm from Java background, folks. That's why I don't really know. And I'm developing in Rust now and C++, so it's a little bit overwhelming to know all the syntaxes languages. So yeah, it's just queue. Everything what you should know that you're using just queue, and why queue? Because of the characteristic of the queue. Okay. Any questions? Thank you. Okay. On the theoretical material, we finished. Like, did I share it? Yeah. Now we are moving to the tree part 2. Okay. Rightmost node of the binary tree. This is also our week. Okay. Let's get started. This is a quite frequent one during the interview. So the problem statement. Return array of the value of the rightmost node at each level of binary tree. Meaning, so we have example. In this example, you're returning first 1, then you're returning 3, then you're returning 6. 6 doesn't have here nodes. Then you're returning, that's why you're returning the rightmost node, it will be 11. From the problem statement, is it clear what has been asked? Okay. At first glance, it might be seen that we can just traverse the right branch until we reach the leaf nodes, right? But it is not true because we need actually return the rightmost. So we must consider all nodes at each level, not just the branch. Once you realize that you are not considering just branch, but all the nodes level by level, because it's intuitive, so the rightmost. You took this one, you figured it out who is the right one. Then you took another level and you're trying to figure it out who is the rightmost in this level. And you took another level and you just need to return the one which is the rightmost in the another level. So you can intuitively understand that probably a level or order traverse will work in this case. Yeah, this is a kind of theoretical material. You can cover it when you will read. There is nothing new from what I just told in the brief introduction to the tree. That for tree level, we will use Q. And that for any another level, so it means, yeah, that we have children of the level second nodes up level 2, 3. Okay. This is basically what I just told, explaining what is the level traverse. Is it clear from here? Why Q and how we leverage Q in this case, just to have visibility to the level. There will be some small.
Sorry, Lydia. You know, after we push the nodes, can you just scroll up a little bit? Yeah, so after we push the node left and node right, why does the queue have only 2 and 3? We did not pop 1, right?
I mean, we pop 1, and then we are adding from the 1 left and right, and that's how we will receive here Q.
So do we have to? Does that mean before we add the children, we always pop them?
Yes. Yeah. See, let's pop the root node off and then add its children to the queue.
Okay.
Let me see. Yeah. So the one difference from the code which I just showed, how we're traversing level by level, a part of traversing level by level kids, we need to track a level in this case, in this task, in order to realize at which level we currently. So this is the difference from the previous code which I just showed. Why we need to traverse, why we need strictly understand when we are into a level. If we will keep adding into queue, what will happen? So from the first iteration, we will add 1. Then we will pop up 1. we will push 2 and 3. If we're not tracking level, at next level we will add. We're still keeping 3, but we will pop 2 and we will add 4 and 5. This is how we'll work just level traverse. But there is some trick, because we need rightmost we need to add rightmost elements, which is 1, 3, 6, and 11 at each level. Means we need to track at which level we are currently. And it is not scoped to this rightmost node. Usually for breadth first search, we need to track what is the level it is. I will explain next task also will be built on the same concept. This is the only one trick which is I'm adding to the traverse level. How we usually track the level of the tree is the same. We're starting our queue, we're building queue, we're adding just root elements. We're entering to our loop with the queue, and there is a level traverse logic. What we're doing in order to track the level? To track the level, we usually take the length queue at the time. So at the first iteration, here will be our 1 size. Means on this level we have just one element, which is we know that size will be 1, and that's how we have understanding when we finish this level. We entering into for loop, which is will be bounded by level size. We're doing what needs to be done from us. Means we are popping our root, we are adding the childs, we're building next level in our queue. And then we are adding logic. If level size at this moment is finished, we know that we finish traversing exactly this level. And in this case, we are adding our node value. We know that this value is exactly the right most in the level which is we are currently working on. This is the only trick which is we are adding here. So at first iteration it will be 1. We took our root. We add here elements, so our queue will looks here 2. Here our queue will looks 2 and 3. We finish this level. We know that we are at the end of size. Means we are adding to our output 1. This node. And yeah, there is we are popping our node only in the nested loop where we're tracking the level. Before entering, so we just measure the size. Okay, now in the second iteration, we will be here 2 and 3. Now we know that our level size at this point will be 2. We again entering the loop. We're processing 2, then we will processing 3. Once we will process 2, here will be our 4 and 5. Will be our 4. And here we will finish. It will be our 4, 5. But still we have 3 here, right? It will be like this. So we still have because we bounded to the level 2 to the size of level 2. We will pop 3 at this moment. 3 will go away. Here we have 4, 5, and we have just one left child. That will be 6 here. So we are adding here 6. We're not adding anything because we don't have right child. And at this moment, we finish with level because we have this check. If the level is finished, on the when we were processing 2, we also had this check. We know that level is not finished. But once we will process 3, we know that level is finished, and 3 is our rightmost node. And we were adding 3. We go out of this nested loop at this moment. Once we will process 3, we have currently our queue, new queue, which is we built, and it is another level, which is contain now 3 elements. And again, we did a snapshot of the size. It is 3. We bound it by 3. We're processing first 2 elements. On each elements, we're checking if we reach the level size. If we reach it, then we are adding this. That's how it works. Is it clear?
So how did we end up determining the rightmost node? Because in the result, we kept appending all the right nodes, right? But we're returning all of this.
So what we're doing at each level, you can think this way. We're using queue, but think this way. At each level, you're actually keeping processing only elements on each level, because you have a snap like size at the beginning that you know. First it will be 1, then it will be 2, and you know where you finish, where finished your level exactly, because
I understood how we are doing that 1, 3, 6. My question was, after this while loop ends, you're just returning res, right?
after this one loop or this one loop.
Yeah, that while loop is done. What do we return? We return res.
Yes.
My question is, res is a whole array. Where do you actually return the rightmost node of the tree?
Here. I'm checking. If
no, this is building the array, isn't it? Like, is res also a queue, or is it an array?
It is array.
So our problem were the problem statement was find the most rightmost node in the tree, right?
Yes.
So where are we returning the rightmost node?
Rightmost nodes.
Yeah, no, not all the nodes. Like the final answer should be 6, I believe. No, 11.
No.
So where do I return 11? Because I added 1, 3, 6, 11 in the array, correct?
No. See problem statement. Rightmost nodes of binary tree. You need to return 1, 3, 6, and 11.
Oh,
okay.
I thought it was final last one. Okay.
No. You need to return the rightmost elements of the tree. So basically, it is this one.
Yeah, thank you. Sorry, my mistake.
No worries. Any questions? Is it clear, folks? It should be clear, because it's quite straightforward. I like breadth first search. Whenever I can use breadth first search, I'm using breadth first search. And it always including a trick with this tracking level. It's not like I explain it here. This is just snip how we usually traverse. You just but it usually comes with the trick that you need to track level. Once you and it will be applied, the same trick will be applied as well for graphs. Quite often you're using this one. So from this you should just understand how to traverse level by level. What does this mean? And remember this trick, how to track level order in breadth first in the tree, and the same concept we will cover in the graph. So if it's understandable. I'm moving, and we will cover another type on the level order traverse. Okay, let's go to the problem statement. Return the weight of the widest level in binary tree, where the weight of a level is defined as the distance between its leftmost and rightmost non-null nodes. I will explain better. So we have this tree. The output will be 7 in this case. Why 7? So let's first understand how to define weight in binary search. So we have this one first level. It is weight 1, and it is number of nodes is 1. Here, the second level, we're taking weight, it is 2, and number of elements is 2. In the third level, we have weight 4. Number of nodes is still 3, but because it's asked between the leftmost and rightmost non-null nodes, we're including null here as well, this one. Usually, I just put it to explain it, but as you see, there is no nodes. But still, the weight of this level is actually 4, because we encounter this one as well. And next, the latest level will also include null nodes here. But here, as you see, there is actually also null nodes, but we are not including it because in our description statement, it's defined that rightmost non-null nodes. So there is, we have weight of 7 elements, actually, including our null nodes. But number of nodes, it's 4. As we can see, the null nodes between the leftmost and right nodes are considering in the weight as well. So,
sorry, Lilia, I didn't understand how the width was 7 in the case where, in the last case.
the last, you don't understand how how we come up with weight of 7 elements.
Yes, with 7. I mean, nodes are the non-null nodes are 4. You said, right?
Yes.
How did you calculate 7?
See, we have this 3, right? It is 1 here. This 2 and 3. Next, we come to the level where actually the left child of this root node is missing.
Mm-hmm.
See, we don't have this root, right? But still, we should consider them. We should, it is a part of weight definition that you should include null elements as well. That's why the weight is actually 4 here, even though we have number of nodes as 3.
Okay.
And now, because here is null element is actually null, but we are including the left child and right child as well. So basically, this the dead tree. You can think it is contains only null elements, which is you can't see here.
Right. So if that node 14 was a right node instead of it being a left node, that width would have been 8, right?
If 14 will be here.
No. If it was the right child of node 7 instead of being a left child,
yes,
then the width would have been 8, isn't it?
Yes,
Okay.
right. Yeah, 100%. Yeah. So the one nuances, which is rightmost non-null nodes and leftmost.
Okay.
Yeah. Everything what is the between should be calculated towards white. So once we understood definition, now we can try to think how we are going to solve this task. So think of data structure like an array where finding the distance between 2 elements is easy. Just subtract the indexes. If we assign similar indexes to the node in the binary tree, we can also calculate the weight between two nodes on the same level. What it's mean? So if we are trying to find the indexes of our arrays, so what we can do in this case, we can we assign the similar indexes to the node in the binary tree, and we can calculate the widest between two nodes on the same level. Look at the way, yeah. So basically, the idea is to put indexes on the whole tree. Once we have these indexes, we can calculate the distance. Distance is actually wide. To using this formula, as we're starting from 0 index, we need to add 1. So the idea is here. So for example, we are working on the level, and we know that the leftmost nodes has index 3, and the rightmost index has 6 here. So we can calculate these actual indexes by subtracting from rightmost index, leftmost index. And it will be our wide form, right? So this is the idea. Is it clear what I'm explaining now? Okay, now that's we're thinking that probably we can solve this way by adding indexes to the elements. Again, if someone will think like why we need to indexes all the elements, why we're just not going and not measuring it on the level of like I explained it with the rightmost. So for example, we can go right. We can take 1, and we know Q is the size 1. Then we are adding right and left child. We know that Q is currently the size of 2. And we can say that y is 2. But actually, because why we need these indexes? Because we need to track these null elements here. And in order to track these null elements, we can just indexes our tree this way. Is it clear what I'm explaining now? Why we can't just use level traverse without indexing? Okay, cool. And with indexing, as I explained it, we actually can, using level traverse, find leftmost element and rightmost element in the level, and we can subtract and find white. Now, if you remember, folks, who was as a part of heap, I believe I covered a little bit during the heap theory, how we usually indexing tree. And so I intentionally included this task because it was a part of theory material, and we never use it as a part of heap. Because we use a heap data structure, we just know that under heap we're using tree. So this is the formula how we usually are indexing tree. And it is intentionally included this task, LeetCode task, in order that you will be familiar if you ever would need to apply this tweak in any tree task, how we indexing elements. So we're taking I, and this, so for example, let's start from root. It is index 0. In order to find left child and third child, we will use this formula. 2 multiplied by 0, it will give us 1. And 2 multiplied by 0 plus 2, it will give us index 2. And if we will continue using this formula, you can find 3, 4, and 5, and 6. Even if element does not exist here, you still will find the index for potentially for potential existing left elements. So
sorry, Lilia, why is I 0? I didn't get that when you're doing 2 into I plus 1.
You're starting from root, right? And you're starting from 0. It applies the same, like in array, we're starting from the index 0. Everything is starting from index 0, right? And in the tree, your root elements will be index 0.
So is I the number for the level?
I, it is your root.
Oh, the index of the root, you mean?
Yes, yes. It could be your parent. You can use this way as well. So basically, because you need to start from something, you can't start in the middle of the tree, right? To indexing it. So you start from root. It is the parent one, and you choose to define his left and right child. Once you define the left child of the root, you can now find for two's root, which is currently 2, and under index 1, you can find where left and right child should be. So you're taking this will be I is 1. You 2 multiply by 1 and plus 1, it will be it will give you 3. 3 and 2 multiplied by 1, it will plus 2, it will give you index 4. And the same here. If you 2 multiply by 2 and plus 1, it will be give you index 5, and it is give you index 6. So I, it is index of the root. Like whatever this subtree or this subtree, they have this one root. They this subtree has 5 in the root. So it root or slash parent of the subtree. Does it make sense? If not, you can just ask again. We have time today for more questions. Okay, so just to sum up, problem statement to find widest binary tree level. We found out what does mean wide. It means that between the leftmost and rightmost nodes, which is not null, we should include even null elements, which is adding actually complexity to our task. Because otherwise we will use just level traverse, and we will snip, we will just snapshot the size of the queue. That's how we will identify the weight of each element. But because we need to keep track even null elements here, we decided that probably if we will indexing our tree, and then we will traverse, we can just easily find by subtracting from rightmost, leftmost index. And again, because indexes is starting from 0, we need to add 1 underneath. So now that we have everything what's needed, we can try and solve this task by using level ordering. So basically, this is the code. We're using queue here, and we need to keep track of indexing. We are not just adding root. We're not just adding any nodes, but we are adding pair of nodes node and pair which is and node element which is associated with the index. This is also quite frequently used because in any tree and even in when you are using devise. So because you need to track, for example, some not only the root, but you need to track, for example, in our case, it is index. Sometimes there is different things which is you need, and then you're including it as a pair here. Sometimes it could be triple even. Is it clear what is this? What is this pair and why we need this pair? Okay, cool. So in the same level traverse, we are entering to the queue. We are traversing queue until it's not empty. With tracking, we again fixed our size in order to understand that we are traversing the level. Then we're popping up our first pair. It is to get value. No, it's actually a head index. Okay, we took the head index here. Why we took head index here? Just it will be left and right most. Okay, current get value normalized. Okay, this is leftmost index. 1 second, I just like level head. We normalize it here. If it's 0, level most index. Okay. So basically, you can ignore for now this one. This way, this will simplify. I think even if you will assign leftmost here, you don't use anywhere. Yeah.
We are using index in the next line, rightmost equal to index.
Where?
Just after, if I is equal to size minus 1, you said rightmost equal to index.
Yes, this is for rightmost index.
But we didn't initialize index anywhere, right? Because
right.
you just deleted that line, which was...
Oh, no, it is here. See?
No.
You mean this one, index?
Yeah.
Yeah, you can just take this index here. It will be int, it will be our index. And here, if current, it will be our current get value. That's it.
Okay.
Yeah, now we can go. So yeah, we're creating pair now. Our key, it will be our root elements, not element, and the value will be our index. So what we're doing here, let's also remove this one because we don't need it. Leftmost you can initialize. It's like even before entering level, I believe. Yeah, because we're taking Q, we're starting a new level. So this code even could be here for left, for initializing leftmost. You can even initialize it here and do not keep it in the loop. But yeah, 1 second. Index here. Yeah, I think this more intuitive for now. So what we're doing here, we initialize our queue. We add our root. Our root will be always 0 because it's 3. It's the same data structure like any data structure. It's usually starting from 0 index. So we're entering our main loop, which is queue, and we keep track until queue is not empty. We fix our first level. We initialize on each level, we initialize our first leftmost and our first, on each level, we keep track leftmost and rightmost, because for each level, it should be different, right? As we understand here. So this will be our leftmost index. This will be our rightmost index. On this level, it will be our left and rightmost index. On each level, we initialize a new one. We're entering to the nested loop where we track, where we're trying to process all the elements on the level. We're pulling our first pair. Is it a pair? Because we have 3 node and integer. So we can take our node and we can take our index. This is quite often used. Also, just remember this one. Now we have knowledge of node and index. We are checking if it's first index, if it's in our nest nest loop. Index is 0, means it's the leftmost elements, because it's just first element in the our level, and we know that it is our leftmost. The same things apply for the rightmost, but now we're tracking if the size is if the size, if we're processing the last element on this level. And there is we just adding elements, keep adding to the queue with calculating our indexes. Here we're using this formula, which is I put above. So once we traverse level, we're going out of our loop, and here this one and this one. Max wide rightmost and levelmost. I think this code should go here. No, it's fine. Yeah, yeah, this one and this one finished. So this loop is finished, and we keep tracking max wide by so. This is also, you should be very familiar, because we quite often using how we're tracking the max value, whatever needs to be found. So we just will keep updating. If we saw so far the max, and it will give us minimum, so we just will keep the value which is we saw so far max. Once we will find the max wide, we will update. If we won't find, then we won't update it. Any questions?
Can you maybe do a dry run on a level where there are like 4 nodes, for example? Because I'm just wondering how this will work. Yeah, I mean, it makes sense, but just wondering how it works on a level where there are like 4 nodes or more. Because the idea is that when we keep indexing the nodes, how do we avoid how do we index the null nodes in between, but avoid the null node to the rightmost? Does that make sense, my question?
Yes. Yes, 1 second. This also not right, because otherwise we won't find the null elements, or we will. 1 second. This will be free. If free doesn't have null, we are not adding. It's here, but anyway, we will calculate this one, which is right. Yes, and then from this one, yeah, we will find. Sorry, Moina, you want just to have dry run, right?
Yeah, the reason for why I asked was I wanted to see, for example, in the last level, you know, I want to see how it's indexing the nodes, the null nodes in between, but it's not indexing the rightmost node, which is null, if that makes sense.
Makes sense. Yeah, let's do this. Let's start from this level. I think, let's see how it will go. 1 second, I just will do for myself. So one, we will go out of this. This will be the first one. Leftmost, we will pop up here. First one, it will be our 1, and it will be our 0 index. If it's 0, so leftmost will be here our 0, and rightmost, because we know the size is over, will be also leftmost will be also 0 here. Now we're taking this node, which is 1. Node 1 is having 2. Here we will put, we will build our queue, which is 2. And if we will calculate here our index our 0 here, we will take, and it will be 1. This is our queue. Next will be another queue. We will take, it will be 3. We will put 3 here. And now we will calculate again index 0, and it will be break 2. But here we have this one. So we will close our queue. We will out of the level. Queue is not empty. We will move to this line of code, and we will see max white currently 0. Initially we initialize to the 0 over here. And now we have our right and leftmost, which is 0, but because we are adding +1 here, so it will update our max white to 1. Okay, now we have here size of 2. Size of the queue is 2 elements. If something is not clear on the during the dry run, just interrupt me, folks. Next, we will pop up 2 here. We're entering the level. Level bounded by 2 size. We're taking it's 2. Here will be our index, which is associated 1. We know that it is leftmost element here. It will be 1. And here it is. We know that the level is not finished, so we will ignore this line of code. Now we have our 2, which is will be 2, 4. We pop up this one, but we still have 3 and 2 in the queue. We will put our 4. Now that here we have index 1, we will make the calculation here. And it will be 4 nodes will be associated with index 3. On this line of code, our code will look like this. We will add our 5, which is associated with 4. We're still in the nested loop. Now we're processing our 3. We are popping up our pair, it is 3, and index which was associated, it will be 2. So we are skipping this line of code, but we are entering to this line of code, and it is 2. We make the same calculation. So we're checking if not left, in this case, for this one, we're skipping this line. Our queue will look like this at this line of code. Why we're skipping, folks? Because the left child for this node is null. Our queue will look like this, and we know that we have right node here. It will be our 7. What was the index? The index was 2. We make calculation 2 multiplied by 2 and plus 2, which just give us 6. So we're ignoring null elements, but because we on each level we are using formula, we are finding actually our rightmost. And we don't include null elements in our queue because we don't need. So it's fine just to use this calculation on each level. And for once we process this level, we know left and right. It will be 2 minus 1, and it will give us the next max wide, which is actually 2. Now in the queue we should have 4, 5, and 7. We process the whole level above. We exit the nested loop. We calculated the max wide. We finish with this and this level. And currently we have this queue, which is we are going to process next. And we know for this level already our leftmost index and our rightmost index, which is after processing level, in which we just building the next level. We can just find our max wide. Actually, yeah, we can just find our max wide. Is it clear? If it's not clear, don't hesitate to ask any questions. Okay. So just track level. Instead of just keeping just node, we need to track, in this case, indexes. How we're doing it, we just instead of keeping just 3 node, we're creating a new object which is tracking 3 node and index associated with this. This is quite frequently will be used, very frequently. This idea, how we're tracking more information than just node. So okay, now we're moving. We finish with breadth first task. You have the idea, the main idea to understand what is the level traverse and tricks which is I show how to track the level. This is all about breadth first search. Now we will move to do quite a complex task, how to build a binary tree. This is something which is also Moina asked me last time. This is not simple. Even with graphs, when we will covering graphs, it is easier to build graphs rather than to build a binary tree. I will explain why it is not easy. So yeah. If we finish with breadth first search, I'm starting with building binary search. It's totally it will be based on the recursion and on knowledge from the previous session. Anyone has any questions regarding the pre-order and in order traverse? We can just quickly come back to the previous session and I will show it. So to build tree, we will use knowledge of depth first search, traversing. As we covered the previous session, it could be a different way how we traverse tree. And we have naming for each traverse. It's either pre-order traverse, in order traverse, or post-traverse order. Depends how we are processing nodes. If we start from processing nodes, then we traverse left subtree and then right subtree, then it will be pre-order traverse. In order traverse, we are first want to process left node, then root node, then right. Maybe here is more intuitive. Yeah. So pre-order. We first process root, then left node, then right node. In order traverse, we process first left, then we process first root, and then we process right. And depends on how we traverse tree, we have different output. In this pre-order traverse, we start traversing from the root of the tree, which is 1. Then we're going left and right, which is 2 and 3. And then we're traversing 4 and 5. Actually, we're processing left, means we're processing the whole level. It will be 1, 2, then 4, then 5, and then 3. Because first root, then left. When we're saying left, traversing in context of depth first search means we're processing the whole left subtree. In order traverse, we're processing first the left subtree, which is starting from 4, because this is our leaf and it is still left subtree. So it will be 4, then we're processing root, it will be 2, and then we're processing right subtree, which is 5. Then we come back, it will be 1, and we're processing eventually right subtree. So this left subtree and this right subtree. This our left subtree, this is our root, and this is our left subtree. In post-order traverse, we traverse first left subtree, then right, and then root. Again, here we process first left subtree, which is 4, 5, 2. And then we process right subtree, which is our 3. And after all, we process only our root. The same apply, so this is 3, it is sub 3. That's why the order is 4, 5, and then 2. Is it clear? Difference. Okay, folks. Now, now in this task, we will ask to. Yes.
Sorry, Lydia, can you just go back one more time?
Sure.
So when we say left subtree, do we start from the bottommost node?
Yes. If it's otherwise, see. Let's focus on in order traverse, right? We need to process first left subtree. It's just a small tree. That's why maybe it's not intuitive. But treat this 4 as a tree, even with one node, but it is 3. So that's why we first process left subtree, which is 4. Then we process 2, and then we process the small tree, which is right. In the global scale of this tree, this one will be our root 1, and this will be our left subtree. So basically, as you can see here, we process first everything on left, going with the small tree, and then we're processing root, and then we're processing right. When we're speaking about post-order traverse, we are processing first left, and then we're processing first right. The same apply for the subtree. Instead of processing root like we did in order traverse, we process first left subtree, then right subtree, and then we process only root.
Yeah.
Yeah, and if you see, this is left on the global scale, this is right subtree, and this are only our root.
Right.
So now, task, build a binary tree from pre-order and in-order traverse of value. So basically, what's we have as input data our arrays, and it's written that these arrays not just arrays, but they reflect the order how the tree was traversed. So that's what I explained it here. Here we have tree and we have output, how we traverse. Now we have this output in our, it is pre-order and in order traverse. We have those 2 arrays, and we were asked to build this tree. There is, the first question might be, why do we need both pre-order and in-order arrays in order to structure the tree? Because, so for example, let's just thinking about in-order traverse when we have just operating with one array. From this array and from the concept how we're traversing, we can actually build a different type of tree here. So let's see on this. We have in order. We can build this tree first, right? We can take 4 as our root, and we can think that this one our left subtree, and this one our right subtree. But we can also take our 3 as a root, and we can see that this is also can be our left subtree, and this one can be our right subtree. So we can, from the in order array, we can build different kinds of tree. Same with pre-order array. If we have, so for example, we take this as an example. We will have 1, 2, and 3. For example, a node could correspond to several different tree. Pre-order helps by providing. We have 1 and 2 and 3. We can, yeah. So basically, with pre-order array, we can go also build a different tree. This is not a very intuitive example. For some reason, I don't know why I put it this way. So we can build, right? The idea is that we're starting from root, and we traverse then left subtree and then right subtree. So in this case, we can build this tree, right? Or we can build actually this tree as well. Like 2. So yeah, from the this array we can build at least those 2 types, but also can be a skew 3, which is on the right. So it could be a 1, 2, and 3. So just from simple arrays, which is give us as an input, we can't really build the tree which is expected. I mean, from one, if we have just in order array, or we have just pre-order array, we can construct exactly tree which is needs to be done. Is it clear why we can't?
I think you're saying that only if we know the pre-order in order, one of the kind of orders for a tree, will we know the order of the elements in the tree. I mean, there will be options like you showed in.
Yes, we can with just knowledge of one array as a pre-order or in order or post-order. We can't build exactly. We can't construct exactly the tree which needs to be constructed.
Okay.
So yeah, that's why usually when you constructed a tree, you are receiving as an input 2 arrays. In this case, we will work with pre-order and in-order traverse. I think there is existing another task, which is with post-order traverse and something else. I don't remember. I will try to find. So in this particular task, we know we have array pre-order and in order, and now we just need to find the way how we are going to construct binary tree. On this point, is it clear? Everything what is needs to be done, and why we can't just use pre-order or in order array? Also, when you will see like input, for example, here, don't be confused, folks. I will show you example. So, for example, here we receive array, right? Usually in the task, but there is trick. We know exactly how to build because we have this null usually preserved. That's how it is. Tree is built here. it's a different technique, because in this case we exactly know that the order, because we keep tracking null elements, which is pointed us to the left or right. Don't be confused. But in this task, and usually in this task, you just have arrays without null. This is the difference between how I just construct in HackerRank task for solving, for reading the input, and this is different because we don't have null elements. Okay. Now to several different tree, preorder helps by providing an order in which nodes are created. Okay. Key idea. Preorder traverse process nodes as. So now we just trying to realize how we are processing. Preorder is traversing root, then left subtree, then right subtree, in order to traverse left subtree, root, and right. So first value in preorder array is always root. Is it clicked? Is it clear why it is always root? Because preorder starting from root. So you can be very comfortable with this and feel 100% sure that preorder it is our root. Okay, building tree. As mentioned above, we know first the value of preorder array. It is 5, and it is value of the root nodes. Now what? If we place root nodes 5, so we need to build its left and right subtree. We will build tree in preorder fashion. Root and left, right. That's work well because the input is preorder array, which tells us exact order to create the nodes. So this will be our main guidance how to build tree. At least from the beginning, we exactly know that tree should start from 5 elements, which is our root. Now we need to find who is left subtree and who is right subtree. In order to find who is left and right subtree, we can use our in order traverse. Because how we're processing in order, we're starting from left subtree, then we're processing root subtree, and then we're processing left subtree. This gives our knowledge that if this guy is our root, 5, means here we have left subtree and here we have right subtree. Is it clear? From preorder, we know the first element root is our root. Now from here, we don't really know who is our left and who is our right, because it could be a skewed tree, and meaning that probably 9 is actually on the right side, and we don't have any left childs at all. Then we can use our in order just to consult. So we know, okay, like we know 5, it's our root. Let's ask in order traverse who is left subtree and who is right subtree. So yeah, the value of the left 5, it's 2 and 9, and 4, 3, and 7 on the right. Since but 9 is left child of the right child, the answer is as we look in ordered array. So if it would be a skewed tree, then in order traverse will look different here. So for example, 5 we will have, and we will have 9 and 2. So for example, 5 and 4. Let's put this way. So in this case, we know if we will have in order to traverse, then in this case, we know that 5 is our root. There is no left subtree on this side, and there is only a right subtree. Means it will be started from 5 and will go 9. But again, we will consult on each step with in order traverse. This is clear. Okay, so next node to place the next number in order create left child of the right to answer. 5 has left sub-3 and 9 will be part of it. So we place 9 next. We will use 2 pointers to help us. Okay. This basically, that's it. What I just tried to explain. Just repeating what I was explaining. So yeah, with this knowledge, we can actually try and build construct our tree. So once we realize that we can keep tracking our root our root parents for tree and subtree from the pre-order array, we can consult with in order by asking, do I have left subtree and right subtree? If I have, then we will try to construct left subtree. Then we will try to construct right subtree. This is just the approach which is we are going to use, and I will explain in the code how we are going to use it. So the rest will be done some optimizations. 1 second. We will use 2 pointers. Pre-order index and in order points to the next node to the place from the pre-order array. In order index help us find where the current root is the in order array, so we can split it into the left right part. This way we can use both arrays to build the tree correctly. Okay.
Sorry, Lilia, before you go into the code, can you just from after you found the left and the right, can you know what happens to 2, 9, and
yes, that's why I'm moving to the code, because from the code it will be intuitive to understand.
Okay, no worries.
Yeah. One thing before processing, I will explain why we are using this private map. Private map is used build a map to get index of any element in order. So it's pure optimization here. We are building our map for in order traverse, just to use it here. So we initialize. We just instead of traversing it here somewhere in our recursion call, to find, so for example, to answer if root value, just abstract it. I explain it why we need to track map. Do not brain yourself what is root value. So we just need quickly to answer in our logic where index is staying from for the elements, and in order to answer it quickly, to instead of traversing the whole array, we will build initially map, which will be associated just to it is index 0, 9 it is 1, 5 it's 2, 4 it's 3. So basically we just associating value of element of node with the index in order sort, just to answer it quickly when we need to find out 9 which index it's belong in order element. So that's it. This is the only role of in order map. Now just let's focus on the how we're going to construct it. So we will introduce a recursion function. Main array, which is we will track, it is our pre-order array. In order array is used only to consult if I have left subtree or I have right subtree. So how it will be started? From this recursion function, first our pre-order index, where we initialize pre-order index here. Okay, it's our global variable pre-order index, and it will be started from 0. I explained it why we need. I explained it now. What is in order map will keep. It's just we just put in order array all the nodes which is associated in the same array with the indexes. Just to quickly answer whenever we need to find the right index into in the in order array. So this the main algorithm is actually sitting here. We will use a recursion, but first this is our base case. For those who was in the previous session, we know that for recursion function, we usually have base case where we need to go out the recursion. Otherwise, we will keep looping in the recursion function. So this is the base case. Where left and right, it is the indexes of the subtree of this one. So this will be our left index and this will be our right index. Once left and right is overlapping, we know that we process all these left subtrees tree and otherwise all right subtrees. Now we're starting from finding the root element, root value for each subtree. So at this one, at the first iteration, there will be 0 index, which is associated with our 5 and 0. We build node because currently we have array just of value. It is now we're starting building our tree actually. So we built root here with element with value 5. Now we need to build the left subtree and right subtree. In order to build left subtree and right subtree, we will consult our in order array where these indexes should go.
Lilia, why did we increment pre-order index when we are, where you said root val equal to pre-order index plus plus? Why did you increment that?
Because on you will see on next iteration how it will work. So this we took from here our root element, this one, and we increased now index. On next iteration, it will be pointed to 9. Let's make iteration. If it won't be clear after dry run, then I will try to explain it better. So now we're entering our recursion function, which is again built. For those, recursion function is the function which is calling itself. So we defined this recursion function. This is our first iteration, and we are calling again the same functions with different parameters at this moment. We are sending pre-order array, which is the same. It won't change. We're just sending the same pre-order array. We will keep sending it. Next, we are sending our left. We're starting from, we took boundaries as a left and right initially, 0 and end of our in order array. So here left will be still 0, but now as we consult here, we are asking root value, we're giving it's 5, and we subtract 1, which is give us exactly this left subtree. That's why we need maintain this in order map. Now we ask, hey, in order map, I have 5 root. Tell me what is the index you have here. It will be 0, 1, and 2. And we know, here. And we know here that our left subtree will be somewhere here, and our right subtree will be somewhere here. What we're doing, we are sending right here. It will be 1. By the way, I put also dry run here as well.
Sorry, I didn't understand how you got 1 yeah.
From in order map, you are giving now this one value. Root value is 5.
Right. So it's -1, isn't it? Because 0 minus 1.
Your root value here 5, which is
okay, in order map, right? Okay.
Yeah, this is in order map, indexing associated with in order map.
Yeah.
But not with pre-order. So why in order map? Because again, we need to find who is left subtree and who is right subtree. That's why you ask in order map, give me index of my left subtree, boundaries of my left subtree. And it will be between 0 and 1 in order map. Now you came here with div pre-order index at this moment will be 1, and it will be 9. From this perspective, it is not a part of recursion function. Pre-order index is the global, and we just keep tracking it here. So now it's 9 and 1. We will build new node, which is root, will be 9 here. And next, we again will call our build recursion function here, which will be 0. And from 9, we will ask, it will be 5, 9, and 2. Okay. Now we are asking root value should be for 9, 1, 1, and it will be 0 here. In this case, we still won't hit this condition because we are not overlapping. They equal, but left is not bigger than right. So we will chance to construct a new node, which will be here will be our 2, because we're just increasing here, and it will be our 2, which will be associated with 2 index. Now we build root here 2. Now we are going into our build function call. It will be pre-array. It will be 0 left, but it will be -1 here. Means we will hit our null. On the backtracking, and we hit in our recursion, means we should backtrack, right? And in this case, we keep creating it's here, right? Our roots. And now, once we backtrack, we start to fulfill our root left assignment over there. So we will reach to the point of the overlapping at this. We will have 2. Once we will come to backtracking to 9, we will have our root 9. And root 9, we will construct as a left child 2 over here, because we told it's here. And next, once you backtrack from 9, you will construct your 5, which is associated with 9 and 2. Is it clear, this part? Once we process it here, this line of code, we will go to our right processing. And we will do the same. So now we build right subtree of 5. We will call our left and right. In this case, it is important. For a left subtree, we're starting from the left index, and we finish our right subtree, we're taking from an order map. And we're doing opposite things, because we know our right, it is end of in order element. But what will be changed this this index. That's why here it is our left. We are consulting in order map, where we are starting our right subtree, and we are always keeping our right, which is end in order 3. It won't never change, right and left, as you saw. We'll go till the end. It will be 0 for sub3, and for right, it will be always end of in order 3. So the same approach we're using for building right subtree, but again, there is as we discussed before, it is not like strictly with we are building our subtree. There will be still calls for a left subtree and right subtree as well. I believe it's not clear, right, folks? But you can ask questions. The main idea in this task, how we're using left and right subtree. Preorder will consult us about root. From the root from the root value, because indexes is different, we will ask an order element. Hey, where is root now? I need to find my subtree and right subtree. That's why we created this map, just to answer it quickly instead of iterating all the time. You can iterate. But this is just pure optimization. We're consulting in order map. Hey, give me indexes of the 5. It's give you 2, and you know now that when you go and build your left subtree, you should go -1, and you should for right subtree you should go +1 from this index. And this you will go. So once you find the subtree, you are going again. You are consulting. You are moving your preorder index. This is your next root of the subtree, because that's how we traverse preorder array. But once you finish 9, you are consulting your subtree. At this moment, you have your 2 and you have your 9. You are processing 9. You don't have right subtree here. It is empty. You have only a left subtree. Same for 4. When we will come to the 4 elements, here we have when we are processing the right subtree here. So we will have our 3. It is not actually 4. It is our 3, and we will ask this. We will work when we will work on this subarray. We will ask, where is 3? 3 is in the middle and has left subtree and has right subtree. Yeah. Yes, please. Any questions? You're on mute.
Yeah, sorry. Thank you very much, Lilia. I'm really sorry. I just don't get this bit about map, and said that we're doing map in order to avoid iteration. So I just wonder if you could do iteration, like just dry run with iteration. How do you go from a point when you figure out that 5 is the root to figure out whether 2 or 9, where they go? What's the logic behind it?
Yeah, sure. So again, map, just think that it is optimization. You don't need to create it. but you always need to find the index in your in order array. You always need to answer what is the index for the element from the preorder elements. This is clear why we are asking, because we know that preorder traversing starting actually from the root of the tree. That's why we will keep as a main indicator of the root elements in any subtree. Starting from 5, the one thing which is we need to know all the time, whether my root at this moment has left subtree or right subtree. Next, for each left subtree and right subtree, if you have, you need to find, you need to construct from the root. You need to find the root. For these things, because we are how we traverse it, we're always processing root. Then we're going to the left and to the right. Okay, I think I understood how to explain it. So preorder index. Preorder index, we traverse first root, then we traverse left, and then we traverse right subtree. Means first index, it will be always our root, 5. Now we need to find, do I have any left or tree subtree? If I have, for this reason, I will ask my in order array, and I will tell it like I'm root, I'm 5. Tell me, and do I have left or right subtree? He will like, yeah, you have 2 and 9, and you have 4 and 3 and 7. From now on, we need to understand who is root, who is our next root for our left subtree and our right subtree. As we are processing root, then left, then right, means next root element should be next element in the preorder element. This one guy is our next root of left subtree or right subtree, depends on what we receive from in order index. In this way, we know that we have our left subtree. That's why, yeah, we know out of these elements in this subarray, 9 is our next root element. Now we need to figure it out if this element has our left subtree or right subtree. For this, we will ask again in order element. Hey, do you have right or left subtree? We don't have right subtree. Is it clear why we don't have right subtree for now, for 9? It's not clear. Okay. Because currently, when we are operating with subarrays, we're processing them granularly. So let me think how to say. We have this root. This root comes from here. Now, because we're using as a consultation in order, we are splitting this array on right subtree and left subtree. Means once we go one level below, we split this array on a smaller one. We are not operating on the whole element here. We are operating on a smaller one. For in order arrays will be splitted on the arrays because they contain sub left subtree and right subtree. On this level, we are break it to the two arrays. Now, when we are working, when we're trying to build a left subtree, we're working only with this array. So we took 5. We ask We know we have left and we have right. We went one level deep. Now, now because we're working on the recursion, so this is kind of things is closed for us. We are not currently working on this. We are focusing on this one. Because this is how recursion is work. Recursion is dropping task on the smallest one. So now we pre-order is a global one, and pre-order index is global one. What we're doing, we're just moving pre-order index to the next element because this is our next root element. Because just how pre-order is traversing. It's starting from root, left, right. For each left subtree, we first will process root of left subtree, right? As I explained it here. So we're starting, this is 1. We move to the left because that's how we support we traverse. But from this level subtree, we're processing first root again, which is 2 here. See, it is 2 here. This 1, this 2 is here. It will be always root. That's why we can confidently introduce pre-order index and just move it on the global level. We move to the 9 here. We know this is our next root in the left subtree. Left subtree because we from in order we know that we have left tree. Okay, we can build next. We can create next node, which is will be 9 here. But now we need to consult again in order array, which just looks like this for us now because we just drop it or we just split it, right? Now we're consulting and our in order array looks like this. We know 9 is root and we ask, does 9 has left subtree and right subtree? In this case, we know that 9 has only left subtree. This knowledge came to us from in order traverse. But why it's 2 and 9? Because we're using recursion function now, and we don't need to care about this part because this is our global right subtree. This is our left subtree. That's why we don't need anymore this knowledge in order to build a right subtree. That's why we're using recursion as well, because we will operate on the smallest array. Once we answer that yes, we have left subtree, but we don't have right subtree, we go back to the we're calling again recursion function, but at this level there will be a new in order array, which will contain just 2. And as we're using recursion function, we will hit this base case once. We will overlap left and right, and we know that we hit our base case, and we will backtrack. This is this characteristic which is we use from the recursion function, and we will start eventually build our left subtree, which will looks like this. I know it is not easy task. This is a hard one. It is include recursion. It is include understanding of how we traverse tree, and so yeah, the main things with the recursion function, I believe, the complexity and the understanding is coming from. Folks, I would encourage you to use this my dry run at each step to link to the code which is I provided. And if it won't be clear, I will explicitly ask next time, and we will walk again. Yeah, just ask, Erin.
Just a quick question. If we were to change it where the input arrays were post order and in order, would it be just a case of you would call the lines, you would call the build for your left, and then you build on the right, and then you just do the 2 lines about the root val and creating your tree node root next? Is it just changing the order of the, is it just changing the order of the code in the build, or do we have to think?
I need to take a look. I need to take a look at my code because it was a long time ago when I was solving with different inputs. As I remember, yes, but let's not overcomplicate this session.
Yeah. Okay.
Yeah,
I'll have a play this week.
Yeah, this one is most popular task compared to the post order.
And the best way to get this really sunk into our heads is to play about with it in code and see how it works. Okay, thank you.
You're welcome. Yeah, folks, don't, I promise if you want to understand from the code and from the dry run, which is I posted, we can walk through next time again. But I encourage you just to take code and link with all steps, which is I defined it here. And I believe it will be, it should click at some point. And maybe at the end of this week somewhere, I will post it how we can construct from different traversals. Just I don't want to bring